We're going to take a little look at inverse functions. I know that these can be a little bit tricky. We talked about them extensively in math analysis, the idea of a function that needs to be one-to-one, because remember, when we take the inverse, it becomes that reflection across that diagonal line, making horizontal lines into vertical lines. So things like parabolas are not invertible functions, so we have to change their domain. We really hit that topic a lot last year, but it was still somewhat of a struggle. And it's going to leak in here today. And there's some pieces there that are a little bit strange. So hopefully, I'm going to go ahead and use the Corpy notes as a stop off on our journey. But hopefully, I'll say a few things a little bit differently. So if something didn't make sense in class, maybe I can make it make sense in here. And I'm also going to break this into a couple of smaller videos, some of them off of Corpy, some of other resources that I have. Anyway, without any further ado, let's go ahead and see what we got here. So remember that what an inverse does is it's something that undoes something else. Like the inverse of an exponential is a logarithm. The inverse of a square is a square root, etc. So when we look for inverses, what's going to happen is like our 2, 5, our F inverse here would be 5, 2. Our inverse of 6, 3, 3, 6 would be 6, 3, etc. And I guess we could go ahead and just finish it off, taking all of the values in my domain and making them values in my range. Now, this one right here is actually fairly significant to look at, because when you go for an inverse, the first thing we do is, instead of thinking about this as f of x, think of it as y equals 5x minus 8. And so for an inverse, we swap x and y. Now, when we go through this, you'd have x plus 8 equals 5y, and then you go and you divide everything by 5 on both sides, and you would find that f inverse is 1/5 x plus 8/5. Now, there's a note down here that says, hey, gee, what just happened? Notice the slope of the original function f and its inverse function here. Those are reciprocal slopes, aren't they? The slope of this one was 5. The slope of this one is 1/5. That's a little bit of an interesting take. And I think if we tried something else, like let's say we had y equals 2/3 x minus 1, if we did a little switch and decided that we wanted to, let's say, multiply everything by 3, move the 3 across, and divide everything by 2, we would find out that f inverse in this case was 3/2x plus 3/2. So notice again, if I started with a slope of 2/3, my inverse function had a slope of 3/2. That is not on accident that those are exactly perfect reciprocals of each other. Now, there's another little thing that's harder to see on these particular problems, but easier to see here, is that if you ever have an inverse, if you draw a dotted line at the line y equals x, so here's 0, 0, 1, 1, 2, 2, etc. If I were to make a nice dotted line, what happens is an inverse function is a perfect reflection across that line. So all of these points are going to just be skipping right across that thing like this. Let's see if I can get this to work just right. And it's going to mirror right along those things as if it was flipping across that particular line. And again, all of my x's become y's, all my y's become x's, and there's a visual thing that happens. Now, the problem becomes, though, when we do that, some of our functions are not going to actually have the right information there, in terms of they have to be one-to-one, and we're going to see that here in a second. So inverse functions have to undo each other. Now, again, in analysis, we refer to this in this way, like f of g of 2 would be 2, or g of f of 9, negative 9 would be negative 9. Or in other words, f of g of any x would be that x in either way. And if you have an inverse, that is what's supposed to happen. Now, again, I'm not going to do the proof in this video of how an inverse actually works, but this is really what is happening. So graphically, we have this idea of something that's flipping across there. But what's cool about that is if your x's become y's and your y's become x's, in your original function, if you had delta y over delta x, in an inverse function, then all of my x's become y's and my y's become x's. The original delta y over delta x becomes delta x over delta y. It just swaps those two x's and those y's. So if your original slope was, say, 3/5, my new one's going to be 5/3. Be very careful. That's not the same as a perpendicular or normal, because that's opposite and reciprocal. This one is just flip it over, and you'll see that right down in here. The part that's a little hard for me, honestly, that I have to say, is when we look at that, if you have a function that looks like this, that is inverse, because notice f of g of x is x, and g of f of x is also x, and you have this story that in the original function f, it goes through a, b, and in this new function, it's b, a, you have to understand that the slope of function g at b is the reciprocal of the function f at a, because keep in mind, a's and b's switch places. So that's really kind of weird. I want to know something about this function g at b, but that means I have to go find out that information about f at a and take its reciprocal. So that's a little bit of a strange idea. So a nice little visual right here is we have the graph of x cubed, which is a nice little graph like this. Here's x cubed. Here comes, so here's y equals x cubed. Why did I write it that way? X cubed. And here comes my inverse function, which is this guy right here, which is y equals the cube root of x. Now keep in mind, those are two inverses of each other. So I'm not going to go very far into this particular video, just kind of going through some ideas. So if we plugged in 2 into the original function, we know 2 is going to give me 8. F prime of x is going to be 3x squared. Not a big deal. F prime of 2 means let's plug in 2 into this original function. 2 squared is 4 times 3 is 12. That's no sweat, no problem. But here's the cool thing. If I want to know the inverse, let's see, let's just keep going here. So if we had y equals x cubed, then x equals y cubed. So that means my inverse function is that y, or f inverse, is the cube root of x. Now, if I want to know the inverse prime of x, then what I could do is I could take this inverse, which is x to the 1/3, and I could take its derivative, which would give me 1/3 x to the minus 2/3, right? And now they wanted me to plug in the number 8, okay? So let's see what happens if I take this inverse right here and I plug in the number 8. So I have 1/3, I'm going to have 8, and I'm going to raise it to the negative 2/3 power. Now this is actually really important to understand. If we have 8 to the 1/3 power, I'm going to get 2. I'm going to get 2. And I'm going to raise that 2 to the minus 2 power. And 2 to the negative 2 power is 1/4. And I got 1/12. Well, what do you know? Look at that right there. That is equal to 1 over f prime of 2. I want to know about the slope of the derivative at 8. So I need to look at the original function at 2. So 1 over f prime of 2 is 1 over 12. That's kind of our overarching story. That's how an inverse works. So with that in mind, if we had this particular story, let's just kind of go through this. F prime of x would be 5x to the 4th plus 2. And so let's say that we wanted to know what happened at 1. So what is f of 1? F of 1 is 1 comma 7, right? That means on the other function, f inverse of 7 would be 1. So if I, let's say, said, well, let's go ahead and find f prime of 1. Then f prime of 1, we already have right here. I meant to say f of 1 was, excuse me, f of 1. On the original problem, let me just back up just a second. F of 1, I get 1 plus 2 minus 1 is going to be 2. So what happens is if I want to find f prime of 1, that would be 7. That means, according to how inverses work, if I wanted to find f inverse prime at 2, I would go over here and I would look at, again, the corresponding value because the inverse switches them. And I would actually do 1 divided by f prime of 1. So even though I'm asking about 2, I have to look at the original problem at 1 right here, which was 7. So I would have a value of 1, 7. That's how it plays. Now, what's very important is before we ever start this question, we were supposed to find out if this even had an inverse. Do I have to change the domain to make this thing work? But an easy thing to do is when you look at the derivative and you think about what we have talked about before. Look at this function. Where would x to the fourth plus 2 be equal to 0? And what you'd find out is it never is equal to 0. You can't. If you raise something to the fourth power, the smallest you can ever get is 0 or a positive number. And then if you add 2, f prime of this thing is always positive. Well, that means this function is a monotonic increasing function. So no matter what it's doing, it is always going uphill. Well, the only way a function could be not 1 to 1 is if the function goes up and then comes down to make it fail that horizontal line test. Well, if it has that, then it's going to have regions of increasing and decreasing. This thing will only increases. So if something only increases or only decreases, it's monotonic, meaning there will be an inverse for this function. However, if you said, hey, I want to know the inverse of this thing, I honestly don't know how to find it. This would be very, very difficult to do. X equals y to the fifth plus 2y minus 1. How am I going to go about finding that thing? I honestly don't know how to do it. So we don't bother. We just go ahead and say, no sweat. We're just going to go ahead and talk about the derivative of the inverse by actually understanding the original function. Okay, example 4, and that'll be the end of this one. So again, we're going to start by looking and finding out, is this in fact a monotonic function? So let's start with saying f prime of x would be 2x to the fourth plus x to the second plus 3. Now again, a nice little feature of this thing is that if you take anything to the fourth power or second power, any value that you do, no matter what, is going to give you a 0 or a positive. So these numbers cannot be negative. They can only be 0 or positives. And then if I add 3, what I can see is that f prime of x is greater than or equal to 0 for all x values, aren't they? No matter what I do for every x value, that's what that says. For every x value, it is always above 0. So it's monotonic. It is 1 to 1. I know I don't have to worry about it, so we should be good. So let's see. If we plugged in 0 to the original function, I get 2. So on the original function, it is 0, 2. So if I want to find the derivative at 2, what I need to do is I need to take the derivative of the original function and find out what happened at 0. So f prime of 0 would be 0 plus 3. And therefore, my derivative of my inverse is the reciprocal of that value, which simply makes it 3. Okay? And I suppose it might be worthwhile to take a look at this last one. They're telling you m of n of x equals x, so m and n are inverses of each other. N and m again are inverses of each other. So my original function is 5, negative 9. So if I want to talk about n at negative 9, then I can do that by looking at m at 5. And what I know is that m at 5 is negative 8/11ths. So this would be negative 11/8 because remember that the derivative of an inverse function is simply the reciprocal of the original function, but you have to switch from the range of the one, because remember n, this is m, n would have the function negative 9 and 5. So if I'm asking about this one at negative 9, then I have to actually look over here at the original function at 5. And that'll be the end of video number 1. All right, see you later. Bye-bye.